All right. Ready to dive into some quadratic equations.
Might not have been your first pick, I get it, but...
Trust me. This is going to be interesting. We're using 4 quadraticequations.pdf for this one. It's got some surprises in store. See, we're talking about those equations.
With the x squared, right? Like x pi syrup plus 2 by 3 equals 0.
That kind of thing. Turns out they're everywhere.
Basketball throws, even those cool curvy designs architects love.
That's right. And the thing about quadratics...
It's not like some new math, you know?
Ancient civilizations, they were dealing with this stuff just...
in their own way.
Okay, so let's get into that. The Babylonians, what was their deal?
Picture this. You're a Babylonian, right? And you've got this...
plot of land. They were amazing at figuring out if you knew...
to sum of 2 numbers, and you knew what those numbers multiplied to.
So like if they knew the perimeter and the...
oh, some field.
Exactly. Didn't have X and Y, obviously, but same idea.
Wow. And then you've got Euclid, the Greeks. Total culture shift.
How they approach it.
Greeks, Euclid especially, geometry was their thing. Imagine those same problems.
But instead of numbers, you're using lines, shapes.
Representing it visually.
Exactly. Euclid found ways to show the solutions, but geometrically.
Amazing how different cultures could tackle the same math.
But in such different ways.
It shows you math. It's not just formulas, it's...
a way of thinking, right. And speaking of different, ancient India, they had their own thing going on.
Right. Brahmagupta, Sridharacharya, big names in math.
What'd they do?
So Brahmagupta, he really pushed things forward, figuring out how to solve...
these equations more generally.
yeah.
And Sridharacharya, he gave us the quadratic formula.
The cheat code, right?
Exactly.
Okay, before we get to that, let's make this real.
Our source, it's got this example with marbles.
Right. Classic word problem.
But it shows you how real stuff turns into a quadratic.
So John and Javanti, they've got 45 marbles total.
They each lose a few, and now the product, what they've got left-t, is 124.
How many did they start with? That's the question.
See, it becomes quadratic because of how multiplying works.
You multiply, you're basically finding the area of a rectangle, right?
So it's like we need the sides of a rectangle.
But we only know the area.
Exactly. And because that area, it's from the marbles.
That's what gets us that x squared, the quadratic.
Like those marbles had a hidden equation inside them.
In a way, yeah. It's about perspective. And that's what makes these equations so cool.
They show you the math hiding in plain sight.
But gotta be careful, not every problem that looks quadratic actually is quadratic, right? Like in our source, example 2, with the toys.
Right. You see that x squared.
And you think quadratic. But simplify it, things cancel out.
And boom, much easier.
Don't judge a book by its cover. Simplify first, then get fancy with the quadratic solving.
Okay, so we've established that you can't just assume something is quadratic just because it looks like it.
But let's say we do have a quadratic equation on our hands.
We've got to solve it.
Right.
Factoring, what is that all about?
Factoring, it's like a puzzle, you know?
Now you've got this big thing.
And you're trying to break it down into smaller, nicer pieces.
Kind of like when you find the prime factors of a number.
But for expressions...
exactly. And the cool part is...
just like with numbers, you multiply those factors back together.
you get right back to where you started.
So example 3 in our source, they use 2x center or 5x plus 3 equals 0.
How do we even start factoring that?
Okay, so the trick is that middle term, that middle 5.
We got to split that up, but in a smart way.
Smart, meaning...
we need 2 numbers, right?
they have to add up to that middle 5, the x term's coefficient.
Okay.
But, and here's the kicker, they also have to multiply to 6.
Which is?
Yeah.
The 2 and the 3 multiplied together.
You got it. The coefficient of the x sot term and the constant term multiplied.
It's like a puzzle within a puzzle.
So in this case, we'd need net equal 2 and net equal 3, right?
Exactly. And then, watch this, we can rewrite the equation.
Like this. 2x by 1 plus net equal 3x plus 3 equals 0.
Okay, I see where you're going with this.
Factor out common terms from each part.
And we get 2x by 1, 3 by 1 equals 0.
And that we can factor even more.
Right. 2 by 3 by 1 equals 0.
Boom. Factor.
And now it's clear. If either of those factors is 0.
The whole thing is 0.
So satisfying how it all clicks.
It is, isn't it? Factoring is great, but...
oh, it's not always the easiest way.
Right. Sometimes those x's, they're just not cooperating.
Exactly. And that's where completing the square comes in.
Ooh. Yeah, our source mentions that.
It's got that problem with Sunita and her age, right?
Right. And that problem shows sometimes you need something more powerful.
More powerful how?
Well, with completing the square, we're basically forcing the equation.
To fit a certain pattern.
We're messing with it on purpose.
In a way, yeah. But it's based on how squares work.
Squares, like x squared.
Right. Think about x plus a when you expand it.
You get x plus 2x plus a.
Yeah.
That pattern, that's what we want our equation to look like.
So that we can
take advantage of it.
Sneaky.
Our source, they use x set sup plus 4 by 5 is the 0 as an example.
We need to add something to make that left side a perfect square.
Okay, so we take that 4, the x term coefficient.
Divided by 2, that's 2. Square it, that's 4 again.
And we just add that to both sides. So now it's x set sup plus 4x plus 4 equals 9.
Exactly. And see what we did? That left side, it's a perfect square now.
We can rewrite it as x plus 2?
Like magic.
Kind of.
Yeah.
And now, square root both sides, x plus 2 equals x to the ma.
And solving for x is easy from there.
Okay, that's pretty neat. But what about the quadratic formula?
That cheat code we mentioned earlier.
Ah, yes. The quadratic formula. It's a powerful one.
Any quadratic equation you can throw at it, it'll solve it.
Seriously, even the really messy ones.
Especially those. No need to memorize it, though.
You gotta know how to use it.
Like having the right tool for the job.
Exactly. Examples 10 and 11 in our source. Good examples.
Rectangular plot of land, consecutive odd integers, classic problems.
Right. The quadratic formula just handles them.
Example 10. You've got this land, right? You know the area.
But you want the length and width, and they're related in a certain way.
It's like a geometry puzzle.
It is. But the quadratic formula, it cuts right through the confusion.
And 11. That one's about these consecutive odd integers.
Those always trip me up.
They can be tricky, but the formula makes it much smoother.
It's like a Swiss Army knife for quadratics. But hold on, we haven't talked about the nature of the roots yet.
What even I asked that?
Ah, good point. Remember how these equations, they can have 2 solutions?
Or just one, or even none at all. That's what we're talking about.
How do we know how many solutions we're dealing with?
Discriminant. That B4AC thing, that's our clue.
I don't even have to solve the whole equation.
Nope. Discriminant gives us a sneak peek.
So if it's positive, B4A0, then what?
2 distinct real roots, meaning 2 separate valid solutions.
Makes sense.
But if it's 0, just one solution. Like the equation is repeating itself.
Okay, and negative discriminant.
No real roots. We've gone into imaginary number territory.
Whoa, that sounds complicated.
Another deep dive for another time.
Right. Sticking with the real stuff for now.
Examples 16 and 17, they show this action.
Exactly.
16, no real roots. Discriminant tells us right away.
No need to even try solving.
And 17, that's the one with the pole in the park, right?
Yeah, like a real world problem.
The discriminant tells us if there's even a possible solution.
That is useful. Knowing beforehand saves so much hassle.
Absolutely. Like having a map before you set off.
Wow, we've covered a lot. Ancient math, real world stuff.
Factoring, formulas, even this discriminant detective.
And we've only just scratched the surface.
That's the exciting part. So much more to explore with these quadratic equations.
There is, isn't there?
But for now, we've got to wrap up.
Before we go, though, think about this.
We saw those examples, the marbles, the land, all that.
Where else in your life might these quadratic equations be hiding?
Keep an eye out, you might be surprised.
And on that note, that's a wrap on this deep dive. Until next time.